Good afternoon and welcome to our Friday afternoon relaxed webinar on energy-based maintenance. We've got going for about 1 hour today, and we've got a great lineup of speakers ready for you. My name is Jared Leake, and I'm the CEO for the Australian Alliance for Energy Productivity. We'd like to commence this webinar with an acknowledgement to the traditional custodians of country throughout Australia and their connections to land, sea and community. I'd like to pay my respects to the elders past, present, into the future as well. And for those of you that are new to A2EP, we are an industry association focused on energy productivity, which is all about getting more value from less gigajoules. And these are our wonderful partners and members that help support us doing such activities and bringing you the latest of technology innovation and thinking of how to improve your energy performance and decarbonise in a smart and fast way. This webinar is being recorded, and we'll have that delivered to you along with the slides early next week. We're looking to take questions. Love your questions. So if you pop that into the Q&A bar down the bottom or the chat box, we'll look at getting to those questions for you. And yeah, if you like someone else's question, feel free to upvote theirs. Joining me today from the A2EP team is Brendan Boss. Brendan is leading our research within decarbonising heat, and we'll hear from Brendan throughout the presentations and at the end of each presentation. But look forward to a couple of slides from Brendan towards the end. But welcome, Brendan. I'd like to start off by looking at welcoming our speakers here today. We have Brad Parsons from Reliability. Hopefully we have Paul Francis from Contract Resources has come through. Brendan I've already mentioned, and Damien Matou from Alfa, Laval. Paul, if you've been able to join us, you did have a few connection problems. Maybe you better hopefully come off the camera, come off mute, and I'll hopefully see that you're there. If there's a problem, we'll forge on and we'll go straight to Brad's presentation. Can't see Paul coming in, so apologies to those that have joined us here. And so let me just flip over. We'll have to, on the fly, we'll change over to presenting with Brad first. And if we do have a problem with Paul joining, we may have to put that one on hold and record that for you all later. So let's kick off and energy-based maintenance. We've obviously at A2EP we spent a lot of time reviewing different technologies of how to improve energy productivity and energy performance. And in terms of return on investment, nearly always number one is some simple activities like behavioral changes, turning things off, or getting controls that automatically turn things off. Very quickly after that comes maintenance in terms of the best ROI for improving your energy performance. And so we thought let's get into this and talk about maintenance. And we're actually going to start now with a very on the high tech side of things. There's some excellent improvements with the way you can do metering and what have you, which really allows you to see the impact of maintenance on your energy usage. And with that, I'd like to welcome Brad Parsons from Reliability. Brad's had over 20 years experience in global technology and working with software as a service and what have you. Absolutely a passionate person when it comes to climate and improvements and energy productivity. And so, Brad, it's an absolute pleasure to have you joining us. We've had some great conversations with you over the years, and now it's great to have you present. So, Brad, I hand over to you to start your presentation and share your screen, and we're all yours.
Thanks so much, Jared. Let's see if we can get the technology working right, and hopefully we can get Paul in shortly. Yeah. We're just going to full screen. Make sure. Do you see the full screen?
Looking good.
Perfect. Thank you. I guess thanks to Jared and the team for the invite and the opportunity to present today. As Jared said, there's a bit of technology in here, but I want to kind of walk through the concepts because I see the opportunity using energy, and there's certainly a lot of people using energy to transform the way they do maintenance, particularly with the advent of AI. So I want to talk through some of those concepts. Obviously, with maintenance, we're seeing this evolution that's going on. We're seeing sort of transformation of existing thinking. New technologies create new opportunities, and those opportunities, obviously can improve the way you manage and maintain your business, but also improve your energy efficiency at the same time and productivity. We'll use some case studies, and if there's questions, quickly, but I don't think we have the opportunity to do that. I guess many of you would have seen this slide on LinkedIn. It's really about this, Second World War, that the planes were coming back from Nazi Germany. They're doing analysis and sort of seeing where the red dots were, and they thought, well, that's probably where they reinforced the planes. But in reality, what was happening is the planes that weren't returning where the red dots weren't. I guess the point of that is that the data you can't see is often more important than what you can. And I think through energy, we're able to light up sort of new sources of data, and that data can create an entirely different picture. And I want to sort of share some examples of that. This is sourced from Road to Reliability, but it's sort of failure patterns that happen in maintenance. And as maintenance professionals, a lot of people would have seen these before, but there's a sort of general premise that a lot of failures happen due to random activities. There's sort of a randomness in why things fail. When you start to introduce the energy metrics, you can actually see things where you wouldn't normally see. And I'm going to go show you through some graphs and material that kind of highlights that. Traditional techniques like vibration and thermography, have been used for 20, 30, 50 years. Using energy as a new dimension really throws that thinking upside down. With the advent of all this data and with the advances that are happening in AI, in the AI space, and this is really advanced, more so in the sort of last 5 to 10 years. Anyone that's sort of seen the press and has used ChatGPT will be amazed. But that's, I guess, that's the front end of AI. But there's a world of advances going on behind the scenes. So injecting energy data in there is just another opportunity to leverage that kind of power and that kind of technology. So I guess if we look back at the way sort of maintenance has been thought of, we can kind of rethink that with the energy lens. I wanted to go back to some basics here. Generally, a machine, when it starts off, has this sort of early phase where it can fail more often than not. It's kind of a wear-in period, if you like. Through the life cycle of the asset or the machine, there's these random failures that I just talked about, and I'm going to describe why that actually occurs. And then we get this sort of end of life where it's worn out, it's done its time. But what we're looking to do is actually improve on those random events that are random, as per the plane example, because there's a new data set or a data set we couldn't see. And we're looking to try and introduce that. In that, sort of life between the early introduction and the wear out phase, these random failures are generally, when you look at the science and the research behind it, one of the biggest contributors are operator loads. You might be a training opportunity there, or maintenance practices, and you can see the list there. And what we're trying to do is actually use the energy dimension to get some insights into why those are happening, and using that data to take that back to the teams, take that back to your contractors, and saying, hey, are we maintaining these correctly? Are we operating these correctly? Can we improve on the work we do? So this is why this energy dimension is so important. Really trying to cut down that uncertainty and make maintenance actually not just predictive, but sort of prescriptive. We know what's going on well ahead of where it is. For those who have been in the maintenance game, this is called a PF curve, and really it kind of maps out the typical ways in which a machine would fail. And this is a generic view. It's not specific to any individual view, any individual machine, or any individual failure pattern. So you can just sort of see that these different behaviors that are exhibited across a typical failure of machine. And you can obviously see that the cost of those increases. The further you go down that curve, the more expensive it gets. that's the known science. And I'm just going to add another dimension to that. So the dimension is when you move down the curve, they traditionally can be picked up by humans. I've got a bit of industrial deafness in my right ear. I can hear it and feel it. If it's very noisy, if it's very loud, the particular machine. But when you're trying to service it, early on, before the obvious signs are showing, then you need instrumentation. And the higher the precision the instrumentation, the more detail you can get, but you need some kind of way to analyze it. And that's where AI comes in, capturing that data really early. And what we see up the top here is you actually see changes in energy. And it makes a lot of sense. A machine will actually draw more power depending on if there's friction in the system that's exhibited as heat, that's exhibited as noise. It will draw more power to kind of compensate for the friction or the resistance in the system. So what we're trying to do is actually measure that energy and determine what's actually changed, or effectively determine root cause. It might be operational change, it might be a slipping belt, it might be a worn bearing. There's different ways in which the machine will obviously fail through operator or maintenance interjection. Later on the stage, you'll see the traditional sort of noise, heat, smoke. If it's at that point, we're in desperate times. This is not the end of the curve you want to be at. We clearly want to be at the front end. So what we're trying to do is measure these sort of precursors, voltage and current particularly. Obviously, that creates not only an opportunity to get it early, but it also creates an economic value. There's value in saving money. I guess some of the quick outcomes, conscious of time, about halfway through. So I guess this is an example of one of my businesses. This is Movis, and this is actually predicting the failure of an air conditioning unit or HVAC unit. You can clearly see cold night starts. This AI is detecting it, and all of that friction, all that resistance in the system is actually drawing more and more energy. You can see quite clearly, in this case, it's vibration and temperature, but that throws off as more energy. Once it's resolved, we're back to normal. But trying to process all of that data without an AI, without a sort of a back-end technology is really quite difficult. Typically in the daytime, we're getting very, not too much to talk about, but it's at nighttime in this particular example where humans aren't traditionally there in this case with the customer. So this concept of 24/7 monitoring, continually looking at different states of the machine, doesn't require necessarily having a human there all the time. Here's some just other examples. Everyone's been to a supermarket and seen one of these, and this is not really a typical example of what you would want to monitor, typically in industrial or commercial applications. We wouldn't go down to this level, but I want to use this as a good case study. So what we can now do through the energy signature is pick up the operational states, or if you're a manufacturer, manufacturing states. Each machine will have its own state and pattern. Each of those patterns has a fingerprint or thumbprint that the energy signature can be picked up and detected. And we might even get unknown states. So these states can really inform the operations. It might be stuck in a particular state and no one wants burnt chook, particularly on a Friday afternoon, I'm sure. So using this sort of technology, analyzing the energy signature, using AI to automatically detect those, creates a feedback loop for operations and maintenance. And obviously different running conditions, you want to know that it's not running when it shouldn't be. You want to make sure that you're not paying extra for when you haven't even got a business operating. So that energy signature is really operating at a level above the metering. We're in monitoring, and then we're sort of optimizing maintenance and production. So that's really a new way in which it's used. We can go down to the next level. This is AI sort of automatically detecting states of these different machines, as we talked about, and there's periods in which it might be transitioning between a state. That might be a defrost. It might be heading into a defrost cycle. If you're a fridge, for example, it might be stuck somewhere in that state. That's, you really want clean running behavior of machineries. And obviously you start to get these clustering effect where the sort of AI and the energy is really throwing off different aberrations or anomalies. If you're trying to manage a fleet, and I've tried to sort of simplify the technology down, but here's a great example. You've got 40 HVAC machines. You can clearly see there's a couple, and this is, I guess, power average over apparent temperature. We can see that there's several machines that are using far more than they should. So this is an effective way to optimize, short staff, to prioritize where your efforts need to be. And it's just using the energy data as a way to do that. Obviously, life cycle is a really difficult thing because you've got maintenance and you've got operation between. Are we extending or improving the life cycle of the machine? That's effectively what we want to know from the maintenance activity. If you start to compare, the energy signatures over time, you can clearly see in both of these examples, with the blue one's the new aircon, the red one's the old. We can kind of see that this life cycle is really changing, and that really great for asset planning, refresh cycles, asset planning cycles. And you can get an opportunity, obviously, to benchmark where your assets are within their life cycle. Obviously, once you start to fix faults, those faults inadvertently actually drawing more power, and they might be faults that you can't see yet. It might be not operating in a faulty manner, but it might be operating in a degraded manner, a manner that wasn't at its peak. You can clearly see examples of this. This is power. It's just tracking normally. As soon as that's replaced, you can see exactly what's going on. It drops the power straight away. And not just maintenance failures, we're also talking about operational states, low refrigerant, because we've got different levels of that. The gas levels are not quite up. So that, again, that's another way to feed back into the operational states and making sure that, maintainers and operators are getting up-to-date information just by adding that energy lens into the equation. Here's just another example, a block filter. Obviously, that happens, more than it should. Using this data, using the energy data, there's more resistance in the system when you add energy into the equation, and that creates, I guess, another opportunity to feed that back into your teams. That was a really quick kind of run through. Conscious, we've got a few presenters today, but I want to kind of share a few examples, give you a view on how maintenance is transforming, how the opportunity that energy presents, and AI and the technology elements of it. Jared, if can do quickly if questions are there, but otherwise I'll pass back to you. Thanks very much for your time.
Thanks, Brad. We'll see if any questions come through in that Q&A box. But great to see that link there, being able to link between energy and maintenance and those predictive parts of that. And Brendan, you've years working with the commissioning and operating refrigeration systems and what have you. Brendan, just wondering if I get your reflections on that one, how you'd see that working with a refrigeration system, because with compressors and oil and what have you, and huge energy use here. So there's really got to be a good link with refrigeration systems as well. Your thoughts on that one?
Sure. Yeah, so there's very minimal out there for refrigeration systems. I mean, it's actually quite basic in some of the things the manufacturers and OEMs do. And there's a plethora of analytic solutions and everything that maybe do some things well and others not so well. And the refrigeration technicians really need something simple that does the heavy lifting on the data for them, because they don't have the time to sit there and process that. So it's great that there is a solution. I wish I had it, 10 years ago. Where was Brad developing this 10 years ago when I was at tools? I would have been your first customer for sure. Because very interesting stuff. So
yeah,
thanks so much.
Thanks, Brad. No questions coming through, but if they do, Brad, feel free to answer them for people to come through. Good one. All right, so let's we'll keep things moving. Next, we want to look at just something straight on the ground where you can make a difference with your energy performance with maintenance. We're not talking initially. The concept is not that high tech, but then once you actually get into the details of how to do this well, I think you'll be impressed. So I'd like to invite Paul Francis to come off mute, share your screen. Paul comes to us from Contract Resources, and without stealing the thunder, Contract Resources is, I'd say, the premier service organisation working across hydrocarbons and mining and things across Australia in terms of fast turnaround and understanding the productivity value of that. I don't think there's anyone much better than Contract Resources. Paul, I'll just get you to change that display settings, because we're seeing the speaker version. If you go up and hit display settings and flick that, swap that over, we'll get to the right one there. Have you got the top in the top left there? Oh, we'll have another crack. The old double monitor, wrong projector, wrong screen. Easy to do. Paul, I haven't got any sound there from you, but the screen sounds good. Nope. Yeah, there, Paul. No, we're not coming through. We're in business. Paul, over to you. Take us through the value of pipe cleaning on energy there. Oh, Zoom is saying it's registered your voice coming through, but I can't hear. Can any other panelists hear, Paul? No. It's got the green box around to say that it should be fine, but I don't know why we can't actually hear you. So it's Zoom is trying. Yeah. No good. Paul, if you want to try and muck around with a few settings there, I might skip over to Damien, and I'll have Damien run through through his presentation there. So if we flip over to Damien, we've got Damien here from Alfa Laval, the biggest heat exchanger company in the world, and with gigawatts worth of heat recovery and heat exchange in Australia. And if you add what Damien's saying to even Shell and Tubes and all types of heat exchangers, yeah, we are talking about gigawatts here. So in terms of energy performance, the maintenance of these heat exchangers is absolutely crucial. Damien, please take us through what can be done to improve maintenance for heat exchangers here in energy performance.
Thank you, Gerard. Good afternoon to all. Can you see my screen? Yeah.
Go for it.
Oh, good. Okay. So I'm gonna introduce energy efficiency with Alfa Laval, the energy hunter concept and the value of service and our tools that we developed. Energy efficiency is one of the main contributors to reaching the targets for Paris Agreement, and is claimed to be our first fuel for decarbonized future. According to the International Energy Agency, energy efficiency accounts for 40% of the potential carbon dioxide savings by 2040. Majority coming from industry and buildings sector, but energy efficiency has an even more important role short term, as technologies are available today. To be on track for net zero 2050, we need to have our emissions by 2030, where energy efficiency could stand for 50% of these emissions reductions. It means it represents approximate half of the abatement in the sustainable development scenario to 2030. So to improve energy efficiency continuously and further, we all need to hunt for waste energy. The purpose of Energy Hunter is to identify the potential for energy savings and OPEX savings, where Alfa Laval's compact heat exchangers can enhance energy efficiency in your processes. We want to change the mindset of ourselves, our partners, and customers to shift focus from only the product and its features to a bigger pictures of values and realizing the impact of lost heat transfer. Therefore, we have launched the Energy Hunter concept with the aim of finding these opportunities, creating awareness, and to quantify and visualize the savings that can be obtained here and now in existing industries. Alfa Laval has technology, expertise, and services needed and is ready to support with maximizing your heat transfer efficiency. Our energy efficient heat transfer solution enable you to save energy and water, improve heat recovery, and reduce carbon dioxide emission in almost every industry. So one of the most important elements to energy efficiency is service and maintenance of heat exchangers. Looking at the graph to the left and traditional performance of heat exchangers, with fouling buildup in the heat exchanger, there is a reduced heat transfer efficiency and thereby performance of the equipment. This results in increased energy consumption, carbon emitted, and operation expenses. With optimal performance and service intervals as shown in the graph to the right, we can reduce the impact of fouling, optimize the heat transfer efficiency over time. So it's leading to increasing energy efficiency, lowering energy consumption, emitting less carbon, and optimizing life cycle cost. This is also why digital solutions for heat transfer have significant potential. It allows us to, us and also our customers, to the insight to take the right decisions. So we see an urgent need for energy savings, but also an urgent need for proper maintenance planning to secure availability of the parts and uptime. So we have developed tools, calculators, and I'm gonna show you one of, it's a light version and it's available on our website, alfalaval.com. I'm just gonna show you quickly. So Energy Hunter calculator, value of service. So on this page, you can choose, select the unit, metric or imperial. You can select the type of cooling system you have, the flow that you are, the type of fluid that you are cooling. So you have a drop-down list and you can select, let's say water, the flow, the design temperature difference, and the present temperature difference. Then if you make up the loss using excess cooling capacity, so yeah, additional chiller capacity, if you increase the cooling water circulation, for example, then you just enter the cost of water, the cost of electricity. If you are part of any carbon credit system like they do in Europe, and then you have the numbers here, the saving in euro, electricity saving, CO2 reduction, and also the water reduction saving. So we just go back. Yeah. So it's a very basic calculator, but we have also developed calculators dedicated to specific application to indicate energy savings, emission reduction, water savings, and payback times. The information can be produced as a report and sent as a PDF for further analysis and discussion with the customers. I just gonna show you one case. So this petrochemical customer was able to increase total output and reduce annual maintenance cost. thanks to a performance audit that led to the reconditioning of 9 M30 heat exchangers. The reconditioning resulted in optimal performance, improved water cooling, and increased service intervals, as well as increased uptime, reduce operating expense, and more sustainable operations. So yeah, that's it for me, Charlotte.
Good one, Damien. Thanks for that. Look, for me, looks simple and easy to sort of do. Brendan, yeah, you've been on the coalface and work with so many different refrigeration engineers and managed companies that look after this stuff. What do you reckon? Easy to use? You think? Could you see people being able to implement that sort of a program and just have a quick estimate there?
Yeah, I think so. I think given there aren't that many tools out there that actually do that, and the data that may be logged on site doesn't possibly tell you if the heat exchanger is dirty easily. So it is nice just to have the performance as it should be in front of you, and it seems quick enough to enter the data that someone on site could do that quite easily. So very handy little reference tool, I think, even in a light version.
Yeah, even if you just get something really quick, and if that helps a little bit of a business case in front of somebody, then away you go. That's worthwhile. Thanks for that, Damien, and great work there with pushing that more service and better energy performance. Thank you. All right, Paul, I'm going to cross fingers here, and when you come off mute, let's hear a noise.
I'm off mute now. Can you hear me?
We're in business.
All right. Now the next thing, I'll try and share the screen.
Yep. And just a quick intro again for Paul. Paul works for Contract Resources, and Paul is the regional manager for Northeast, which is Queensland and Papua New Guinea, and comes to us with a electrical instrumentation trade background. So, and Paul, we love talking about metering here, but not today. We're going to get into the actual impact of cleaning and some different methods and things like that. So, love for you to take us through it.
All right, thanks for the second introduction. So I really appreciate it. Yeah, Contract Resources. So I'll just spend really quick 2 minutes just talking about who we are. So for those that don't know us, we're a specialised industrial services company. Do a lot of industrial cleaning, specialised type of services. So the main ones around catalyst handling, hydroblasting. We do rope rescue around turnaround services, so large shutdown works, and one of the services we have is specialised pipe and tube cleaning, which I'm going to focus on today around pigging processes. So in this preso, I'll just talk a little bit about pipeline cleaning and the different methods of pipeline cleaning, and then a few case studies and examples of where we do that, and specific relation back to energy-based maintenance, and you know, how the blocking of pipelines, etc., can certainly lead to higher energy consumption. So if you just think about a pipeline, I suppose, like we have here, this is a lot of what we see in pipelines around the industries we work in, slowly get blocked over time. And as you can imagine, if you're driving your car on a straight road, nice fuel efficiency, but as soon as you head into the wind or go up a steep hill, you're going to increase your fuel usage significantly, which is similar to when you have a pipeline that's getting blocked. You obviously need your drive at the end is going to be using more current or more diesel to run that flow through the pipeline, and you're going to be running more inefficient. So when we talk about pipeline cleaning, there's many different reasons for pipeline cleaning. It can be just scale and sediment build-up, or you may have flow restrictions. You might be preparing for maintenance and repair, or you might want to do some integrity inspections. And then there's several different methods of cleaning. So high pressure water blasting, flushing, so just volume flushing, or chemical cleaning, or mechanical pigging, which I'll focus on today. So when choosing the method of cleaning, there's a few different things to consider. Firstly, the pipeline material. Is it a poly pipeline or a steel pipeline or fiberglass? It's all those factors are going to be different for the method. The length of the pipeline. Is it a short 10, 15 meter pipeline, or is it a 20 kilometer pipeline? So clearly different lengths. And internal diameter can be as small as a heat exchanger tube right through to a large ductwork. The application of the pipeline, is it running air, water, oil, etc., and expected pollution. So if we're expecting a scale build up, sediment, wax, etc. And the configuration of the pipeline, is it going up high head pressure and going up hills or over hills? Does it have lots of bends, etc.? And then the history of the pipeline, has it had process upsets or leaks or blockages, etc. So once we do get to a point where we think that pipeline pigging is the best method for cleaning the pipeline, then there's still some more factors to think about. So dewatering the pipeline, the different type of pigs is the foam-based pigs on the left there. So they're generally used for dewatering pipelines or removing sediment or bacteria from pipelines. Or the middle ones, the hard body pigs, are a little bit harder. We'll pull out wax deposits or thick oil sediments, etc. And then the one on the right, they're sort of the specialist pigs that we use that have metal inserts in them, and they're really good for hard coke deposits in oil heaters or very hard scale in larger pipelines, which we'll run through some of those examples today. And then once we've chosen the type of pig that we want, we can also choose a different type of propulsion. So we can either send the pig through pushing with air or nitrogen, and that's good for light products or dewatering a pipeline, but it does come with high risk because you can lose control of the pig speed with the amount of pressure that can build up behind the pig, and then shoot it through the pipeline really quickly. So it must be done with a lot of care. We can vacuum the pigs from one end to the other, so suck it through, and then all the whatever's in the pipeline can be pulled into a vacuum truck or a vacuum bin. So really good for if you can't create any waste, it minimises the waste level, and it's good for removing liquids from pipelines, etc., and minimising that waste. But the most common propulsion for pigs is the water pump. So water doesn't compress, so what you put into the pipe is going to have a proportional effect on the pig, and it's going to be consistent speed and high control of the pig throughout the pipeline. So now I'll just talk a little bit about some of the projects that we've done around Australia and New Zealand, etc. One of the common projects that we do pigging for is fired heaters or in oil refineries, Australia and New Zealand. And we decoke these. So as you can imagine, a fired heater in an oil refinery goes through a hot box. The oil runs through a hot box to heat up the oil, so it comes in cold and comes out the other end warm. Now, as it goes through there, it does the oil heats up and provides a coke sealing on the pipeline, and over time that coke build-up gets worse, and then that obviously the heat transfer through the pipeline reduces, so the inefficiencies run through, so you're using more fuel to burn for the heat and less heat transfer through your oil. So over time we need to clean those pipelines. So generally the heaters around Australia and New Zealand are on a 2-year basis, so we do that pigging on a 2-yearly basis across the oil refineries, and those passes for those pipelines are anything from 3-inch up to 8-inch. And as we know, the oil industry across Australia is getting lower, so some of those heaters have come offline now, but we still do heaters across Australia on a regular basis. Geothermal, so over in New Zealand we've done a few projects with the geothermal, and as you can see the photo on the bottom left there, quite a significant build-up of silica in those pipelines. So the silica over time running the water through those lines, it does have high silica. And as you can imagine, as that build-up of product on those pipelines builds up, you need a lot more energy to run your engines or your motors to be able to run that fluid through those pipelines. So it does make the major flow restrictions and causes higher energy use in your pipelines. So generally we've done DN300 or DN350 pipelines around 300-meter runs, and use the specialist pigs for those sessions. And it's really hard build up of silica, and we've been able to remove those restrictions and get it back to full flow for the client. In the alumina industry, we do quite a lot of different pigging throughout the alumina industry, and one of the common ones is the waste pipelines from the plant through to the red mud dams. So really important pipelines for the plants, and generally the red mud dams are a little bit away from the plant, so it might be 15 to 20 k's away. So those pipelines can run, over hills and through gullies, and they're quite large pipelines. So the ones in this photo, 2 of the DN750 pipelines, they're quite large. As you can see, the pig that they're loading there, quite a large foam-based pig. These pipelines are about 15.5 kilometres, and they do build up. You can see the bottom left-hand photo there. It builds up with scale, so that's after about 12 months of operation. If that was left like that and the pipeline come offline for any particular reason and sat in the sun, the pipe does tend to move or expand in the sun and then retract at night, and that scale can break off, and then the next time you start the pipeline up, that scale all builds up and then can cause a blockage. So really important to clean these pipelines on a regular basis and minimise the amount of energy used for those large pumps as well that are pumping that product through. So we clean them on a 2-yearly basis. And just a side note, I suppose, we also completed intelligent pigging of these pipelines, and these pipelines are basically at the end of their life, and that intelligent pigging integrity inspection was able to defer 20 million of capex for those pipelines as we proved that they didn't need to be replaced. A lot of it was still in good working order, so that was a big positive for the client. This is one of the main pigging jobs that we do, is alumina refining and the JPU cleaning. So the jacketed pipe units. So these are pipelines with steam tracing to heat the product in the pipeline. And there's 14 JPUs at these facilities, and there are a series of 6-inch pipelines, so 3 of 6-inch pipelines, in a single pipe. And they're about 1 kilometre long with about 30 bends. So in these pipelines, the scale build up in these pipelines is extremely hard, and it's aggressive, and it builds up very, very quickly. So as that scale builds up on the pipeline, you need a lot more steam to be able to get that heat transfer through to the product. So over time, it becomes inefficient to run that pipeline more than around 9.5 weeks, which is what we've found. So each 9.5 weeks, we take the client takes those pipelines out of production, and we clean them on a critical path program, and then put them back online and move to the next one. And that's an ongoing project that we do. And we do about 60 to 70 pigging cleans per year. And we've really gotten really good at that. And it's definitely the decisions around that 9.5-week cleaning schedule is based on the efficiency of the plant, and the heat transfer, the amount of steam we need to use to be able to get that heat transfer through to the product. So very much an energy-based decision making on when to do that maintenance. Similar one, or I guess a bit different one here, is the oil refining. So this is an example of vacuum pigging, where we've used vacuum to clear sludge from pipelines. So some product got into a Jet A1 pipeline in the oil refinery that we worked at. So it was a 24-inch pipeline. So we installed launchers at both ends and set up dual vac trucks at one end with a sludge bin, and pulled the foam pigs through that pipeline to be able to clean it. So that was a really efficient process of cleaning that pipeline. And then the final one here, this is a really important one for the alumina refinery. They had some clarifier lines, 350 lines, which the pipelines transfer product from one part of the plant to the clarifiers, and they generally use 2 pipelines, and over the 10-year period where these lines were in production, they slowly but surely built up a lot of internal scale and really hard scale, and they progressively got worse and worse and worse to a point where they usually have two pipelines online, and they have a spare, but they had to run all 3 pipelines at max flow just to get the output through these pipelines due to the product buildup. And then, you know, we had to try and, obviously, because they'd left it way too long, then we had to bring one pipeline off at a time to be able to clean it. And then obviously that was a production impact. If we'd done it earlier, we wouldn't have had that production impact, because we could have had a line offline in the secondary state. So yeah, as you can imagine, these the pumps running these pipelines were all running flat out, and which they shouldn't have been. They should have been running at, you know, half of their capacity, but they're running at full capacity. They were significant flow restriction, about 30 to 40% loss. And in the end, we cleaned all 3 of those pipelines successfully, and got the flows all the way back to nameplate flow, and a bit above actually. And I guess when we talked about energy usage, we weren't able to get a full data of the energy reduction that we were able to provide, but certainly from the client, they said it was a significant reduction in their energy usage, and obviously they got full production back on their plant as well. So now, when we talk about, you know, the decisions around maintenance, if you leave it too long, then clearly you're going to use more energy and you're going to cause production upset. So we always encourage the clients to make a decision early. Don't wait until it becomes a major problem. Do it early and have that preventative maintenance set up. That's it from me.
Thank you, Paul. How often are they're getting the reports back to say, yeah, and this is how much less energy is on the pumps? You know, this was a 1 megawatt pump here, and now it was drawing 1 megawatt or so, and now we're back down to 800 kilowatts. I mean, do you often get that sort of closing the loop of that energy reduction?
Not as much as we like, so we certainly do. We do ask for that feedback, and like in this case, we really wanted that feedback, because you know, we want to put in our final report and those sort of things. But they certainly gave us some high level numbers, but not to the detail that we would like. We did see some graphs, but we didn't have a lot of info, and yeah, some clients were reluctant to share that with their contractors. But yeah, we would have definitely liked to close that loop more often than we do.
And that makes me think about Brad and the technology that Brad presented earlier. And I'd assume sometimes maybe they don't have the data there being captured to be able to close the loop for you. Brad, you must see that as an opportunity and think, hey, contract resources, I could probably help you out here and put a bit more value on that maintenance you're doing, yeah?
Absolutely, Paul. Let's have a chat. Lots of energy. Those pumps are enormous, and those pipelines are pushing a huge amount of product through. So, yeah, good call, Jared. Thanks.
Yeah, perfect. Good. I thought let's kick it home with our very own Brendan Voss here. Brendan, you've been thinking about maintenance and energy on refrigeration systems and heat exchangers as well. You got a couple of slides there to show us the way you've been thinking about it, and some technologies and things you've been thinking about and working with.
Sure, no worries. I feel inherently smarter now listening to all those presentations. So hopefully I do a reasonable roundup, but I will get through some quicker because we did cover some of this ground previously. So I sort of come from a chiller background, main chilled water plant, and a lot of the fouling happens on the condenser side of the system or a coil side of the system. So focused a little bit there. So just some really basics for anyone that's not aware. There, on top there is a refrigerant to air heat exchanger, and on the bottom is refrigerant to water at a really basic level. I put a really nice picture here of something we were building when I was in my last company, of just how that bottom heat exchanger looks, to put some premise around all those little holes where copper tubes go through and get filled up with water. So that's going to premise my next slide. And as we saw before from Alfa Laval, there's a lot of people will know and recognize these just plate and frame heat exchangers we see in plant rooms. So this sort of argument is or argument about maintenance is similar for both. So basically from my end, being a real simpleton here, material and surface area to make sure they're suitable for the fluid basically, and has enough surface area to transfer heat are the main two things. So let's assume here we have a chiller running and I want 7-degree cold water, and my refrigerant and I have nice clean tubes, which don't look anything like those big pipelines we just saw. These are nice and clean. The refrigerant is 6 degrees. And when they're dirty, we'll have water at 7, but our refrigerant will be at 4. What does that mean? Well, the efficiency measure we call in this industry is thermal approach. So that's just a measure of what the difference is between these two temperatures. So in this case, 1 versus 3, the right-hand side 3 being much less efficient. So what we're doing here as a summary is just we've reduced the surface area and we've increased the amount of mechanical work that the chiller has to do. And why this is important is you can also impact capacity that you can deliver, because we're just not getting that heat transfer, and it often goes unnoticed. So I really wanted to do this slide. This was my favorite one. Here's a nice clean tube that runs through a heat exchanger. Nice little grooves on the inside, which increases surface area. Typically 100% capacity, 100% efficiency when they're clean. But when I make a nice little bit of scale over the top of those, we can get anywhere at an extreme to 70% of the capacity and drop to about 80% of the efficiency as just a rule of thumb. So here we come along with our nice tube brush, which goes very well with that pipe cleaning we just looked at, except much less advanced. We become nice and clean and back we go, basically. So we've picked that 20% back up. Now, how you monetize that in terms of the maintenance, I mean, the maintenance is often not very expensive. I mean, that sort of tube cleaning exercise is often less than 1 day of time for a chiller technician to do. So let's assume that this plant is performing at $140,000 a year. If I lose 5%, I'm at $147,000. So there's my $7,000. That 1 day of labor now seems very cheap because I'm just going to keep that happening. And so on and so forth, all the way down to the point where you can be 35,000 plus very, very easily if you're running that plant quite regularly. So the point here is if we just assumed we hit 5% loss and that no one ever picked that up and we never fixed it from year 1, we would lose $105,000 in 15 years. So that is quite substantial, makes my maintenance costs seem now very cheap. Just looking at it from a different perspective, looking at a motor, people often miss this. Also, if we have a 15 kilowatt motor, at 50%, we should consume very, very limited amount of power. Like let's assume we have a very nice accurate meter from Brad. Brad's done us a good job and put a very nice accurate meter in, and we're pulling 2.2 kilowatts. This can be over $500 a year just on one pump alone, and it could just be some grease on bearings or something very, very simple, right? And we don't really need fancy analytics or anything to generally solve this problem. I guess the lack of data and translating that data is often the biggest gap. So there's a nice little affinity law. You can literally program that in a normal controller and pick that up. It doesn't need anything too fancy for this one. So I just did a really quick one. Often at the equipment, if we do lose efficiency, right, let's say these coils are very, very dirty in a heat pump, we're going to need to push more water and we're going to need to use more energy at the heat pump, like we just said before. Nice and simple. When we go to a water-cooled chilled water plant, my condenser tubes are dirty. I may not notice that for quite some time unless I am a chiller technician, which is always fun, and I'm there to do the maintenance, and then it's hard to come by people actually in the normal maintenance that will look this hard sometimes at some of these issues. So what might happen here is my fan energy will certainly go up because the control system will try and ramp to meet my previous set point, but my chiller energy could stay static because my cooling towers just might run a bit harder, and I might not ever realize that that's actually happening. So, and my pump energy will be flat. So the anomaly is the fan energy increasing, and Brad's example before, that sort of data would definitely find this very, very quickly. So how did I used to do this as like without all that data is we used to pick up the manufacturer's data sheets and we just used to look at touch points to say really simply at 100% load at this temperature, we should use this. Even if you have only 4 data points, you can still do something, even if it's a little bit basic. And if you wanted to get really fancy, we used to run regression models on our own equipment and we would put them in the chiller controller to identify when we were reading higher power. So that's that fancy little 3D graph down the bottom. So last piece of advice, I guess, from me is that if you have a BMS, use it to do some of these basic checks. You can often just do rule-based approaches with metering platforms, or if you want to get very fancy, then go and talk to Brad, because that's probably the next level here, but there is some real basics that do get missed. So I guess I just wanted to quickly get through those before the end of this. So, and that's it for me.
Thank you for that, Brendan. Brad, I think there's another one for you. All right. And look, let me throw another one. I went to a Maltworks earlier this year, and they had a bit like an extraction fan, and out nearby that fan, it led into the air intake for a condensing coil, and it was absolutely chock-a-block that I don't know how they're getting any airflow through there at all. And I'm like, well, yep, no one's been monitoring the energy impact of that one. And there it is, and from what Brendan's showing there, that impact on that energy performance must be quite dramatic. There it is. Okay, and that brings us to pretty much the end. I haven't seen any questions or anything coming through. Let me just double check. But everyone's going to get the contact details of the people here today. You'll get the slides, you'll get the recording. That'll be out next week. And if you've got some more questions, please do reach out. Paul, thanks for that. A great lesson on pipe maintenance and what have you, and the potential there. Thank you so much. Damien, heat exchangers, great little tool. Thank you. And Brad, you've got the technology. Let's see that implemented more widely. Love to see that take off. So thank you so much for joining us, to our audience. This is our final webinar for the year. Thank you so much for being with us through the year. Hope you'll have a very safe and happy festive season. And we look forward to kicking off a webinar series. Probably it'll be in February next year. All the best to everyone, and thanks again for our speakers, and I hope you have a nice afternoon. Thank you.